for us to record. Okay, so we're recording. We're going over the solutions for worksheet number 6. And this is the last problem. This is an AP style problem from 2009. And here in part C, you're being asked to use a left Riemann sum with subintervals indicated by the data in the table to approximate the integral from 2 to 13 of f of x dx. Show the work that leads to your answer. So if you look up above, the table has 5 data points, 2, 1, 3, 4, 5, -2, 8, 3, 13, 6. If you want to plot them, go ahead. You can. You don't need to necessarily. But I'll do that anyway, just for sake of visualization. So if I were to make a quick sketch. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And it looks like all these y values are, well, some are negative. So 1, 2, 3, 4, 5, 6, and 1, 2. Okay, so 2, 1 is a point right here. 3, 4 right here. 5, -2 right there. 8, 3 right here. And lastly, 13, 6. And if it's twice differentiable, we would assume it's going to be continuous. So if you want, feel free to, connect these if you want to. I don't really care. But the bottom line is that we have to do a left Riemann sum using these subintervals. So the first subinterval is defined from 2 to 3. You got 4 subintervals, by the way. If you have 5 points, the number of subintervals is always n-1. In fact, if we go back to our notes for 6.3, no, actually it was 6.2. Lecture notes, filled out notes, 6.2. Remember, I did state that the number of subintervals is always n-1 when doing a Riemann sum. So let me go back to the image again. Sorry about that. So we have 4 subintervals. The first one is going to run from 2 to 3. And it's a left Riemann sum, so you have to have the left corner touching. The next one is going to run from 3 to 5. So again, it's the left corner touching. The next one is going to run from 5 to 8, and again, it's the left corner touching, so it's actually going to look like this. And next is going to run from 8 to 13, and again, it's the left corner touching, so it's like that. So you're finding the area of all these regions here. Find this area, this area, this area, and that area. So that's visually what you're doing. Question in the chat. Oh, so great question. How does the left Riemann sum influence the way you approach a problem? Because if asked for a right Riemann sum, I would draw my rectangles differently. I'll talk about that in just a second. Hold on to that thought. But I'm using the left corners. So when I work this out, I find the width of each interval. So 3 minus 2 is delta x1 times f of x1. I have to use the y coordinate at x equals 2 because that's where the left corner is of that interval. So when you're doing left Riemann sums, you're actually not going to use all the y values. In fact, you ignore the last y value when you're doing a left Riemann sum. When you're doing a right Riemann sum, vice versa, you ignore the first data point and use the other 4. So that might help answer the question, but I'll do a quick visualization afterwards to show how you do this as a right Riemann sum. So again, delta x1, you have that times f of x1, which is the y value at x equals 2, which is 1. So that's going to be the first rectangle. Then the width of the second interval is from 3 to 5, and the y value there is 4. That's where you're doing 2 times 4. Then the next interval goes from 5 to 8, so width is 3, and the y value there is -2. And then the next one, the width of the interval is 5, and you're using the y value of 3. And you add them up, and you get 18. So I am going to ask a question like that on our exam. So I'm glad I'm recording this, that you guys have this as a good example. And now if I did as a right Riemann sum, the only difference, you keep the same width of the intervals, but the only difference is that you're not going to use these values you see. Instead, you're going to be using the right endpoint. So now I'm going to put 4 here, -2 here, 3 here, and 6 here. And if you wanted to visualize it, let me erase some of these things here. If you want to visualize it, what you would do is you would, let's go to green, is you want the right endpoint to be touching. So you have that, you have that, and you have that. So you can see how the first rectangle, if it is a right Riemann sum, it's going to have the area of 4, which makes sense because 3 minus 2 times 4 is going to give us 4. Next one's going to be obviously a negative area. Then it's a positive area after that. Then a much bigger area after that. So that's how you treat difference of right Riemann sum. Great question. Let's talk about another image. So look at this one here. There's also a good problem that I could ask on our test about average value. So here first I asked to evaluate this integral using areas. So you're integrating from 1 to 7. And notice how I chopped this up into 3 regions. So I had a right triangle here, a normal triangle here, and then a rectangle down below. And I labeled those 1, 2, and 3. So area of region 1 is 1/2 times base times height, 1/2 times 1 times 2, so just 1. Area of region 2 is 1/2 times 2 times 1. That makes sense. And area of region 3 is just going to be the rectangle, which is 6 times 1, or 6. Add them up, you get 8. Done. So find average value. Remember, average value is 1 over b minus a times the integral of a to b of f of x dx. Well, we already evaluated the integral from a to b of f of x dx. That was 8. The fraction part, 1 over b minus a, well, my a and b are 1 and 7 respectively. So 1 over 7 minus 1 times 8, 8, 6, or 4/3. Then you're asked to do this again, but translate the graph 2 units up. So you're adding 2 to the function. Well, that's one of the properties we've talked about. You could, when you do that, you just, integrate it like you usually would. You integrate from 1 to 7, you integrate to 2, and we've done integrals of constants. That's just the constant times the difference of the width of the interval, which is 6. So 8 plus 12, 20. And then the average value, you just do 1 over b minus a times that integral, you get 10/3. So that's how you would want to go about something like number 6. Use geometry, use area. Remember, if it's average value, then just take the integral and multiply by 1 over b minus a. Easy peasy. So hopefully that's okay. And then another problem that I did, actually, I just want to look at number 5 one more time with you guys. This right here, I believe. Yeah, just look at this one more time because I think I rushed it last class. So I could ask something like this too. Again, just using area. So if you integrate from 0 to 2, remember, if you're integrating from 0 to 2, you're looking at a quarter circle. So area of a circle is pi r squared, the radius is 2, but it's a quarter circle, so you do 1/4 pi r squared. And below the x-axis, that's why you have to have a negative there as well. That's why it's negative pi. For part B, you're integrating from 2 to 6. From 2 to 6, I'll do that in green. Well, that's just a triangle. So the base is 4, the height's 2, 1/2 times 4 times 2, that's 4. If you're going from -4 to +2, I'll do more of this in red. You have a semicircle with a right triangle. Well, there the right triangle is easy. It's 1/2 times base times height. Your base is 2, your height's 1, so you have 1/2 times 2 times 1. Semicircle, 1/2 pi r squared, so 1/2 pi 2 squared, because radius is 2, right? And if you work that out, you get 1 plus 2 pi, but both those regions are below the x-axis, so you put a negative out in front. For D is just combining B and C, right? The red and the green regions. The red region was -1 minus 2 pi, or negative parentheses 1 plus 2 pi. But I distributed the negative, so I made -1 minus 2 pi, and then adding 4. Combine like terms, you should get 3 minus 2 pi. For E is absolute value, meaning that anything that's above the x-axis anything below the x-axis becomes above the x-axis. So essentially, these flip. So now you're doing this. Everything's all above the x-axis, so I'm making everything green here. And so you take whatever you got in part C and do the opposite sign, make a positive now, make it 1 plus 2 pi, and add the 4, so you get 5 plus 2 pi. That's an absolute value transformation, which you guys have seen before in pre-calculus. And then for F, and we had in our summer assignment many months ago, a few months ago. And then for F, you have fx plus 2. So you break it off, f of x, 2. We know the integral of f of x from part D was 3 minus 2 pi. For the integral of -4 to 6 of 2, remember 2 is a constant, so it's like a horizontal line. So you're integrating from -4 to 6 of y equals 2, so it's 2 times the difference of those upper and lower limits, which is going to be 10. So 2 times 10 is 20. Combine like terms, you get 23 minus 2 pi. So again, I'm not going to give you a question like this with 6 parts and expect you to do that 10 times. That's not fair. What I'll probably do is I'll give you a diagram like this and have you just do one thing and say, tell me this thing about it. So, but I'm going to ask you something like this where you have to use some geometry. And then Ms. Valk is working on the solutions for 1, 2, 3, 4, so you have it for your reference. But let me just give you guys the answers really quickly. And then I'm going to put you guys up back in another breakout room to do more practice. Let me actually go back to the worksheet. So for number 3, really quickly, let me do this in light blue. You're going from 1 to 9, but there's a -2 there. So you're going to do -2 times -1. That's why it's just 2. For B, you're going from 7 to 9 of F and H. We have F and H separately. 5 plus 4, you get 9. For C, you're doing from 1 to 7. We have it from 1 to 9, and we have from 7 to 9. So remember, the integral from 1 to 9 of f of x dx equals integral from 1 to 7 of f of x dx, as well as the integral from 7 to 9. Oh goodness, sorry for missing handwriting. Let's redo that. I can do better. Plus 7 to 9 of f of x dx. Excuse me. And so the integral from 1 to 9 is -1. The integral from 1 to 7, I don't know, call it x. The integral from 7 to 9 I know is 5. So if you work it out, x should equal -6. So that'll be -6 for this one. That's using additivity property. Then here, from 7 to 9, 2 f of x and 3 h of x. Well, you multiply that by 2, so that's going to be 10. Multiply h of x, that integral from 7 to 9 of h of x, 3 times 4, that's going to be 12. Final answer is -2. Wait. Oh my goodness. I did 2 with you guys a long time ago. Okay. Sorry if I'm repeating my efforts. Let me just do 3 and 4 really quickly and give you guys more problems. If you see a different variable here, that's just 5. If you see √3 and a different variable, who cares? That's just 5 √3. If you reverse it, a different variable, big deal. But make sure you reverse -5. And if you have a negative out in front, -5. Yeah, sorry, I don't know why I did 2 again with you guys. That's good, I guess. Actually, I think what I'll do is I'll probably wind up taking a quick screenshot of this when I'm done. Here from 1 to 3. So you have from -1 to 1 and from -1 to 3. So remember, -1 to 3 of h of r dr will equal from -1 to 1 of h r dr, because you're given that. So it means that the remaining part will be from 1 to 3 of HRDR. Well, -1 to 3 we know is 6. -1 to 1 I know is 0. 1 to 3 I do not know, but that's going to be 6. And if you reverse it, so this is interesting. They change the letters, big deal, doesn't matter. Totally arbitrary. But they reverse the limits of integration and they put a negative. So it's actually, they're doing negative of -6. So what from 3 to 1 is -6, but it's also another negative. So it actually comes out to being just 6. That one. And really quickly, if you remember, that was 0. That was reversed. That was -8. That was 3 times from 1 to 2, so that's -12. And from 2 to 5, remember we have from 1 to 5. We have from 1 to 2. So that's going to, if you have from 1 to 2 is -4, then from 2 to 5 is going to be 10. That one. And let me box these other ones here. And let me get my screen capture tool. So we'll put this in a more neat and orderly way for you guys here. Worksheet number 6, number 1 through 4. Okay. So I'll make sure I'll show it to you guys in just a little bit. Anyway, so that was really good practice. So now let me show you the other documents in the test review folder. Oh, let me stop recording.